students, my name is Chaitanya, Physics faculty at Shakthi International School. Today, in this video, we are going to learn about an important topic of class 12th, chapter Wave Optics. Okay, the topic name that we are going to see is Young's double slit experiment. Okay, so now before going any further, okay, in general, let us understand what is a wave. Wave is a disturbance created in a medium. How do we define the equation of a wave? We know wave equation is a function of both x and t. From class 11, we know that we can write the wave equation as a sine kx minus omega t. This as our equation. Okay. Now, if you are having two waves, you can write y1 is equal to a1 sine kx minus omega t, kx1 minus omega t. Okay, y2 can be written as a2 sine kx2 minus omega t. In these two equations, if you observe, these two equations have same frequency because omega is same. Omega is nothing but 2 pi f. If omega 1 is equal to omega 2, that implies frequency 1 is equal to frequency 2. That means wavelength lambda 1 should be equal to wavelength lambda 2. Okay, so these are the outputs. Okay, so when the wavelengths are equal, they should have same color. When the frequencies are same, we are calling coherent sources. Okay, now since you know there are two equations of same frequency and same wavelength can be written in this form. The amplitudes are different. Okay, so whenever we are talking about Young's double slit experiments, it actually explains you how a light is acting as a wave. Okay, experimentally it is observed that when we are taking a single source, okay, we have taken a source here. Let's say this is your source. From the source, if the light is coming out, now to make sure that those two light rays which are coming, two waves which are coming from that source are monochromatic, we are taking one arrangement in which two slits are provided so that the light rays which are coming from it will be having same wavelength and frequency. It is also going to have same wavelength and frequency. Okay, these two are called slits. Now slits are just a gaps, two different sizes. Okay, this is having a distance of d from here to here. This is having a distance of d from here to here. One small gap is there in that plate. Okay, in that sheet that you are taking there. Now we are taking a screen. Okay, at d distance. Okay, at capital D distance from this. Okay, and we are observing, experimentally it is observed, there are certain dark and bright fringes which are forming here. Okay, so there is a bright fringe which is forming here and a dark fringe which is forming here. In this way there are certain bright and dark fringes which are forming. Now this dark and bright fringes are the results of intensities being maximum and intensity being minimum. When do we have light rays meeting? When they are meeting, if the interference is constructive interference, then we know that it is maximum brightness it will give. If it is destructive interference, then they cancel each other, so there will be no brightness, only darkness we can see. So this is a property, the interference is actually the property of a waves. Now if that pattern is actually being observed here, that means light should have a wave nature. This experiment practically proves that light is having a wave nature. Now this is your experimental setup. Let us understand what is happening in it. So instead of drawing a 3D, I'll draw a 2D picture here. So these are two different slits we are having. There are conditions for observing this interference pattern as well. So this is your screen on which the bright and dark fringes are actually forming. the distance from here to here is taken as capital D, and the distance between two slits are taken as small d. Now, light rays will be coming from here. They can meet at this particular point. When they are meeting at this particular point, okay, we have understood that constructive interference from class 11th and destructive interference will happen at particular path lengths and particular angles. Okay, we know that constructive interference will occur at delta phi and destructive interference occur at delta phi, which is equal to pi, 3 pi and 5 pi and so on. Constructive interference will occur at 0, 2 pi, 4 pi and so on. Okay, I hope you remember these. If this is the condition, we know path difference can be written as 2 pi by lambda into phase difference can be written as 2 pi by lambda into delta x. So delta x is equal to, if you want constructive interference, it should be 0 or lambda or 2 lambda, or in fact you can take it as n lambda, where n value will be ranging from 0, 1, 2, 3 up to n. In the same way, destructive interference, when you are observing, delta x should be equal to lambda by 2 or 3 lambda by 2 or 5 lambda by 2. This is the value, or if you are writing a general form of it, you can write it as 2n minus 1 lambda by 2. 2n minus 1 lambda by 2. This is the general form of it. Okay, where n value will be ranging from 1, 2, 3 up to so on infinite, and here n values will be ranging from 0, 1, 2, 3 and so on. Now if you observe, these two particles, these two waves are actually meeting at this particular point. The distance from here to here can be written as d by 2, and the distance from here to here is also d by 2. We know this is capital D. So this distance can be written as under root of d square by 4 plus d square, and the same distance, this can be written as d square by 4 plus d square. Now this is your x1 path traveled by the initial wave, and this is x2 path traveled by the second wave. If you are trying to understand what is the path difference, x2 minus x1, it will become 0, because since both the distances are same. Now, if path difference is 0, we are going to observe a constructive interference. That means you are going to see a bright fringe. Okay, we name this bright fringe at delta x equal to 0 as central maxima or central bright. Okay, now further, this is the first maxima. As I told you, there are several others maximum brightness fringes which are falling on that entire screen. Where can be the next bright fringe? We have to analyze that now. So again, the same setup is taken. Two slits which are allowing a monochromatic light to pass through them, and a screen at a distance d. Okay, to understand the screen at a distance d, to understand the formation of bright and dark fringes. Now let's say this is your central bright which is forming here. There is a first bright which is forming somewhere here, first bright. If the first bright has to form, then the two light rays which are traveling from here to here should meet here, and they should form a constructive interference. Now let us assume, now there are certain conditions in which Young's double slit experiment we can see interference pattern. That is, the value of d should be which very big compared to that of small d. Only and if this condition is satisfied, then only we can see the pattern of interference. If it is kept very close to it, we cannot see the interference pattern. Okay, let's say the angle that you are having here is theta, then if you are drawing a normal from here to here, making an angle this to be 90, this will be theta. If this is theta, you are having one right angle triangle. This is how we are having it here. This is your 90 degrees. This is D. Okay. This is the delta x, because if this is x1, this total length is x2, then this distance from here to here is what we are taking it as delta x. So this is delta x. This is your angle theta from the alternate angles being equal condition we have taken. So if this is theta, obviously the angle from here to here also should be theta, because we are consider them as parallel lines. Since they are very far from each other, they are acting as a parallel lines. So this angle will be theta. This angle will be 90 minus theta. So the remaining angle again you will be getting it as theta. Now from these expressions, from the triangles, okay, from this triangle you can write sine theta is opposite by hypotenuse. Opposite is delta x, hypotenuse is d. You can write delta x is equal to d sine theta. In the same way, from the right angle triangle that we are taking here, this is your theta. This is the distance. Let's say the distance from here to here is taken as y. This is your y, and this is going to be capital D. From this expression, tan theta can be written as tan theta is equal to y by d. Now you know, if theta is very small, then sine theta is almost approximately equal to tan theta. Okay, and there is a limit. Theta should be less than 30 degrees or equal to 30 degrees. Okay, so now since D is very big compared to that of small d, we can use this. So from here, delta x divided by d will be equal to y by capital D. So y can be written as d into delta x divided by d. So if you want to understand where is the first bright that will be forming, y first bright, okay, you have to take delta x for the first bright. Delta x for the first bright will be lambda. Delta x for 0 means this will be central bright. Okay, at lambda you will get first bright. At 2 lambda you will be getting second bright. In that same way, delta x is equal to n lambda we can take. So y bright, first bright can be written as lambda into d divided by d. Okay, y nth bright in the same way can be written as n d lambda by d, where n is the number of bright fringe that we are talking about. Okay, in the same way, when we are trying to analyze dark fringe, okay, y dark. In y dark condition, delta x formula is 2n minus 1 into lambda by 2. So that means y general dark can be delta x into d divided by d. This is a general formula. In place of delta x, you can write 2n minus 1 into lambda d divided by 2d. This is a general formula for dark fringe. If you are asked first dark, okay, if you are asking first dark, then you can write d lambda by 2d. Okay, if you are asking second dark, you can write 3d lambda by 2d. In this way, we can find where there will be a bright fringe, where there will be a dark fringe. Okay, so this is what being observed experimentally, and this is what is analyzed later mathematically. Okay, so that means, let's say whenever there is a slit, double slit, you will be having a central bright. After central bright, you will have a first dark. After first dark, first bright, because the distance from here to here is d lambda by 2d, and the distance from here to here is d lambda by d. Okay, in the same way, 2d lambda by d, 3d lambda by 2d, in that way you will be getting, and the same dark and bright fringes will be forming on opposite sides of the central bright as well. This is your first bright, this is your first dark. That means the distance from here to here is also d lambda by 2d. Distance from here to here is going to be d lambda by d. Okay, we can find what is the distances between two different darks, two different brights, or one a dark and another bright on the same side of that central bright or on the opposite sides of the central bright by using this general formulas. I hope you understood this concept well. We'll meet in the next video. Thank you.